Okay. Now here we have a choice. Such a rectangle I is not unique. You can take many such I. For example, I can also take this I. Okay. Can it happen for some I, the zero extension is integrable over that I. For other I, it is not. Can this be happen? Using the lemma we just proved, we will see that this will never happen. If you have a rectangle which is the property, then all rectangle containing D has the same property. Okay. So to justify this definition, we still need to verify that if I prime, that is I prime here, is another rectangle, then we set J to be the intersection of I and I prime. So J is this rectangle, which the saddle. This red saddle rectangle is our J. That is the intersection of I and I prime. So this is a rectangle containing D. D is also contained. This is a rectangle containing D. Then, by the previous lemma, we see that FD is integrable over I if and only if FD is integrable over G. Because I contain G, right? Therefore, using our previous lemma, we see that FD is integrable over I if and only if FD is integrable over G. Because the zero extension of FD considered as a function of G is precisely the zero extension of F considered as the function of D. Okay, maybe I need to write it in more detail. FD should be FDG. Okay. So using this result again, so FD is integrable over G if and only if FD is integrable over I prime. Therefore, the integrability of the zero extension over I and over I prime is the same. So this means that the integrability does not depend on the choice of I. Okay, and as to the value of the integral, we see that FD over I equal FD over G. And again, this is equal to FD over I prime. So the value of the integral also does not depend on the choice of the rectangle I. So this justifies our definition of integrability of F over D, and also justify to define the integral of F over D to be the integral of its zero extension over a rectangle containing D. Okay. Now we will study another important result. This is a theorem. D is bounded, and F and G are integrable over D. So for general bounded subset, we have already defined the integrability. Therefore, we can assume that F and G are integrable over D. Then the result is that if F is not greater than G, then the integral of F over D is also not greater than the integral of F of G over D. the second result, linear combination. Suppose alpha beta are real numbers, then the linear combination of f and g is also integrable over d, and the integral of the linear combination is the linear combination of their integral. So the second property we have proved for integrable function defined over rectangle. Now we generalized this to the general bounded subset D. Okay. So the first result is very easy because the zero extension of f outside D is also not greater than the corresponding zero extension of G. Therefore, the integral of D over f over D is precisely a larger extension, the integral of the zero extension over a rectangle. Then for integral over rectangle, we have this greater than GD, the zero extension of G. But this is precisely the integral of G over D. So this proves the first result. For the second result, so this is our D. For the second result, we take a rectangle I containing D. We take a rectangle I containing D, and we observe that alpha f plus beta g, the zero extension of the linear combination, is precisely the linear combination of their zero extension, as you can check. So if a point belongs to D, then both functions, all these three functions on this equality, the right hand side and the left hand side, we have three functions. All these three functions are evaluated at the point in D. So this is the usual equality. And if a point x is outside D, then both sides of this equality are zeros. So this means that this equality always true in the whole Rn. In fact, we only need this to be true in over D, over I. But actually, it is true for all points at every point in Rn. So as you can check, we have this equality. Maybe I will write the part of this proof. So for x in D, our alpha f plus beta g dx is alpha fx by definition of zero extension plus beta gx. But fx is precisely f dx. Okay? Because x belongs to D, so the value of the zero extension and f coincide. Similarly, the gx is precisely g dx. So this proves the equality for x in D. If x is not in D, you can prove in the Schmidt method. And in fact, in that case, the computation is zero. Okay? So anyway, this equality is true. So using this equality, we see that alpha f plus beta g is integrable. Because f and g are integrable over D, which means fd and gd are integrable over I. So therefore their sum, that is the zero extension of alpha f plus beta g, are integrable over I. So that is alpha f plus beta g is integrable over D. So the integrability is proved. Okay. Now for the equality of this integral, just compute d alpha f plus beta g, that is the integral of the zero extension. But the zero extension is precisely alpha fd plus beta gd. And for integral over rectangle, we have the linear property. That is the integral of the linear combination equals the linear combination of the integral. So this is fd plus beta gd, that is alpha f plus beta g, proving the theorem. Okay. The next result, so D is bounded and F is also bounded. A bounded function you can consider as a map from D into an interval. Here B is positive. That means B is upper bound of F, and the minus B is the lower bound of F. So this will be convenient to write a bounded function in this way. Then our conclusion is that if D has Jordan measure content 0, then F is integrable over D, and the integral is 0. Okay, this is the first property. The second property is that if D is the union of D1 and D2, and F is integrable over D1 and also integrable over D2, then F is integrable over D and also integrable over the intersection of D1 and D2. Moreover, the integral of F over D equals the integral of D1 plus the integral of D2 minus the integral of the intersection. Okay. So in particular, if the intersection has Jordan content 0, then according to the first conclusion of this theorem, the integral of F over the intersection is 0. Therefore, the integral of F over D is precisely the sum of integral over D1 and D2. Because according to the first result, the integral over D1, the intersection of D1 and D2 is 0. Okay.